Now that we know how important these redox reactions are, we're going to take the next steps to figuring out the energy output of these redox reactions. But before we start off on that process, there are some key principles or key things that we need to have a be aware of before we get further deeper into this topic. So when we say that we're going to measure the output of these redox reactions, what we are referring to is the fact that we're going to measure the output coming from these redox reactions in terms of voltages. Okay, and that means that you're going to measure things and the quantities are going to have voltage as the units. And if you remember, if you've taken some physics, high school physics, you will remember that voltage is commonly referred to as potential, and it's typically indicated with the letter E. And so therefore, we're going to use the same convention. We're going to call these outputs as potentials, and then we're going to use the letter E to indicate those values. Okay, the short notation that we use is this letter E. Okay, and then what are we measuring the voltage for, or what are we measuring the potential for? So we're going to measure the potential or the capacity of the reaction to undergo reduction. So we're going to measure the voltages of reactions undergoing reduction, and we're going to denote them with the letter E. And because we are measuring these voltages for reduction reactions, we're going to call them as reduction potentials. And again, the letter E continues because that's the letter that we're going to use to indicate these reduction potentials. So let's say that we have a whole bunch of reactions, and then we have measured these reduction potentials, and we want to compare the capacity to undergo reduction for a whole bunch of reactions. If we want to do that, then we have to make sure that we measure these redox potentials, the reduction potentials, under a set of standard conditions. And therefore, and we're going to actually do that. We're going to measure these reactions, the capacity to undergo reduction, we're going to measure that under a set of standard conditions. And therefore, we're going to refer to these number that we're measuring as standard reduction potentials. Okay, and when we talk about standard reduction potentials, if you look at the symbol that we're using for these standard reduction potentials, you'll see that it comes with letter E, just like what we said before for voltages, and it's going to come with this E naught at the top. The naught indicates that it's a standard reduction potential. So to differentiate it from non-standard or non-standard reduction potential, we're going to use this E naught, because whenever you see this E naught, it tells you that these voltages were measured under a set of standard conditions. Okay, now what are those conditions and how are we going to go measure the voltages is what we're going to focus in this section of the video. So how do we measure these standard reduction potentials? And you can see here that E comes with the E naught. So that tells you that we are measuring standard reduction potentials. So before we make the measurements, we have to be aware of what the standard conditions are. So in order to measure things under standard conditions, we're keeping these things at these fixed values. We want to make sure that if we ever use hydrochloric acid or any acid in these experiments, we want to keep the hydrogen ion concentration to 1 molar. Independent of which acid it is, we want to make sure that the hydrogen ion concentration is set at 1 molar. And then if we are using any solutes, when I mean solute, things like ions and things like that, if we want to keep their concentration also at 1 molar. And we want to make sure that the pressure of the reaction under which this reaction is taking place, we want to keep the pressure under 1 bar, okay, at 1 bar. So if we keep it at those conditions, then we know that we are under a set of standard conditions, and then that's the starting point, and then we let the reaction do whatever it does, and then we let the reaction undergo get to equilibrium. Okay, so these are the things that define our standard conditions. Now that we know what our standard conditions are, now we're going to focus on how we're going to make the measurement. So you see this picture here on the left side. You see two sets of beakers, and on one side you have one set of solution, you have another side, you have another set of solutions, and they're connected through this wire. Okay, so that's what we see. So an important thing to know about these measurements is that, so anytime we want to measure these potentials, we want to think of it something like, when we measure our height. So let's say that you say that your height is 5 foot. How does somebody know that your height is 5 foot? you need either a ruler or a tape that has markings on it saying, okay, if you're this tall, it's 1 feet. If you're this tall, it's 2 feet. If you're this tall, it's 3 feet, things like that. So that means anytime you make a measurement of height, you need some sort of reference point, and your measuring tape or your ruler or something is going to serve as the reference point. So same way, when we measure these standard reduction potentials, we're going to use something as a reference, and that reference is going to be our standard hydrogen electrode. So how is the standard hydrogen electrode made up of? The standard hydrogen electrode is made up of 1 molar hydrochloric acid solution. If you remember, we said that if you're going to use any kind of acid in there, the concentration needs to be 1 molar. So we're going to use 1 molar HCl. And then we're going to put in gas here, hydrogen gas, through this electrode. And it's not 1 atm, it should be 1 bar. So we need to put in hydrogen gas at 1 bar. It's going to be flowing through it. And then it's going to flow on this platinum electrode. So this wire is platinum wire. This is actually made up of platinum wire. It's very inert. It doesn't react with anything. And then you have a platinum electrode over here. And then the hydrogen is coming in. And this is our setup. And one of the assumptions is that one of the assumptions that is made according to convention is that this standard hydrogen electrode is set to give us 0 volts as output. So that means it doesn't contribute anything to the voltage output for our redox reaction. So this standard hydrogen electrode's output is set to 0 volts, and this has been set as a fixed number. So that means that this doesn't contribute anything to the output. So now to this standard hydrogen electrode on the other side, we're going to connect any reaction for which you want to find the reduction potential for. So in this case, we're trying to find out the reduction potential for what happens when you have copper 2 plus, which accepts 2 electrons to become copper. So we're trying to find out how much voltage is generated from this copper 2 plus reaction. So what we are doing here is we take this beaker, fill this up with 1 molar copper 2 plus solution. Could be copper sulfate, copper nitrate, something like that. But the copper 2 plus, the copper there is in copper 2 plus charge. It's going to be filled with 1 molar concentration of that solution. And then you're going to dip in it a copper metal, which is the copper wire, and it's going to be stuck in that solution. Now that copper wire is going to be connected all the way to the voltmeter, because the voltmeter is a device that's going to bring these two electrodes together, and it's going to measure the movement of electrons. The electrons from one reaction to another reaction is going to be happening through the wire, and we're going to measure that using a voltmeter. And then if you look in the middle, you see this salt bridge. The salt bridge serves the purpose of, if there is any imbalance in the amount of anions or cations in this reaction, the ions are going to travel through the salt bridge, either from this side to this side through the salt bridge like that, is going to come out this way, or is going to go through this way and then come out through this way. So you're going to have some ion trafficking that is happening. That's going to make sure that the circuit is complete, and you're going to make sure that there is not a significant imbalance in, like, okay, on one side you have lots of cations being produced, on the other side you're going to end up having lots of anions that are being produced. Because if you remember, any redox reaction is going to have an oxidation half, which is going to be losing electrons, and then a reduction half that is going to be accepting electrons. So whenever things are accepting electrons, you may end up creating a lot of anions. Whenever things are losing electrons, you may end up too many cations on one side. We want to avoid that sort of an imbalance. To kind of make sure that that balance exists, we have this salt bridge, which is going to help those excess anions move from one side to another side of the cell. So it's going to set up this way. You connect the electrode to the voltmeter. The salt bridge is there. You let the whole system come to equilibrium. At that point, you measure the voltage that you get from the cell, and the voltage that you get from the cell, in the case of copper half reaction, it's going to be 0.34. If you remember, if you see a value here, the value of the voltage that you're seeing here only comes from this half of the cell, because we know that this half of the cell gives us 0 volts. This is not going to give us any voltage output. So whatever you're reading there is the voltage of that particular half reaction. Okay. And if you need to find out the reduction potential for, let's say, silver half reaction, then you just replace this part of the cell. Instead of having a copper wire, you put a silver wire and then dip it into a silver solution, and then you measure the voltage for that silver reaction, and then you will get the voltage value for the silver reaction. And this way you can keep changing just this one half of the half cell, and you can just keep measuring a whole bunch of voltage values. And this is exactly what people did. And then when they measured it, they created a table of values. And this table of values is called standard reduction potentials. When they measured it, you can see that the hydrogen half reaction is at 0 volts, and because we set this to 0, and this is our standard hydrogen electrode. And then you can see that there are certain values that are positive values, and then you can see that there are certain values that are very negative. So the general rule of thumb is that if you get more and more, if your values of reduction potential are more and more positive, that means that those reactions have a very, very high tendency to undergo reduction. If your values are less positive, less and less positive, then they have lower tendency to undergo reduction. Okay, so higher the positive value of the reduction potential, standard reduction potential, you know that those reactions are going to have a higher tendency to undergo reduction. And remember, the title of the table says standard reduction potential. So that means don't ever get confused by this, because the title itself says it's standard reduction potential. That means all the reactions that are in this table are all reduction reactions. They are all reduction reactions. So these half reactions are all reduction reactions. They are all reduction. There is no oxidation reaction here. Everything is a reduction reaction. And you can also see that every reaction has the same kind of setup. An ion plus accepting electrons to become the metal. Here is an ion with a +3 charge accepting 1 electron to become Fe2 plus. So you can see that we know that reduction is defined as the process of accepting electrons. So all of these are processes where the thing on the left side of the arrow is accepting electrons to become the thing on the right side. So we are measuring the standard reduction potential, or the capacity of the reactions to undergo reduction. And more positive these values are, higher the tendency to undergo reduction. Okay, so this is the take-home point from measuring standard reduction potentials. Okay, so now let's think about the reaction that we looked at before we started learning how to measure standard reduction potential. So the reaction that we were looking at was, okay, we started with our silver nitrate solution with copper wire dipped in it. After a little while, you can see that there is silver deposited in this region, and so on the solution turned blue in color. And we were saying that the reason why this turned in blue in color is because initially we had only copper metal, and then over a period of time it changed into copper 2 plus, which is blue in color. And then this deposit that's happening here is because this silver ion gets converted into silver. Now the question becomes, why does silver ion change into silver? Why does silver ion get reduced to silver? And why does copper get converted into copper 2 plus? What is the underlying reason for that? To understand this, we're going to use the standard reduction potential for the two half reactions that are involved in this particular overall reaction. The two half reactions are, one is going to be relating copper to copper 2 plus, and the other half reaction is going to connect Ag plus to Ag. Okay, so we're going to write it down and then write down the voltages for those reactions. So for the copper half reaction, the Cu2 plus 2 electrons going to copper, the E0 value is positive 0.34. For the silver plus electron going to silver, the E0 value is 0.8. And if you remember, we said when your reduction potential is higher, when you're comparing two reactions, that particular reaction has a higher tendency to undergo reduction. So that's the reason why silver in the presence of copper is able to get reduced to silver, is because this voltage plus 0.8 is much greater than 0.34. So that is the reason why silver ion, silver Ag plus Aq gets reduced to Ag. That means if Ag plus electron is going to go to Ag, then what needs to happen is, so you can have both of these reactions undergoing reduction. Once we know that this is the reaction that's going to undergo reduction, then this is the one that needs to undergo oxidation. So if you want to write the oxidation reaction, we actually have to flip the reaction and then write it left side to right side, and that's going to signify our oxidation reaction. Okay, so first thing that we are understanding in this process is, once you list out the potential for the two half reactions, we understand why silver is going to undergo reduction and why copper is going to undergo oxidation. Okay, so now the question becomes, so if this reaction were to happen, what will be the net voltage output that we are going to get from this particular reaction? How do we get the voltage output out of this reaction? Okay, so if you want to get the voltage output, you really have to create two half cells, one for copper, one for silver, and then connect them through the salt bridge and connect them through the wire, just like what we did for the measurement of standard reduction potential, and then you will be able to get the voltage output. So what is the voltage output we're going to get from this particular reaction? So the first thing that we're going to write down is the way we want. So what we said that this particular, the bottom reaction is going to undergo reduction, right? So this particular reaction here is going to undergo reduction. So the Ag plus reaction is going to undergo reduction. So we want to keep this as it is. So we want to keep the reaction as it is, but we're going to flip this top reaction and then we write it down. Okay. And let's do that. So if you do that, so you can see here, the copper 2 plus is now flipped to copper solid is the copper reaction is flipped, and we have written this as opposite of this particular reaction given here. So now we have written this as copper solid going to copper 2 plus 2 electrons. But when you flip the reaction, we also have to change the sign of this voltage, and we change that to a negative 0.34. We've done that. And then we kept the silver reaction as it is, exactly as it is. But the one thing that we have done when you're writing it here is that before we kind of write the overall reaction, we have to make sure that both half reactions have the same number of electrons. So if you want both reactions to have the same number of electrons, the way we can make them have same number of electrons is this reaction has 2 electrons. If you want this reaction to have 2 electrons as well, we multiply the whole reaction by 2. So 2 Ag plus 2 electrons plus 2 Ag is going to give you 2 Ag. So we multiply the whole reaction by 2, and that's what we're writing over here. So we've written the reaction after multiplying the 2 electrons. And when you multiply the 2 electrons, you should not multiply the value of the voltage, because the voltage output is going to be 0.8 volts, whether you write it as Ag plus electron going to Ag, or whether you write it as 2 Ag plus 2 electron going to 2 Ag. The amount of voltage that is coming from that 1 electron transfer, or 1 electron accepting, one electron being accepted by Ag plus, is going to be the same exact value. So we always multiply the equation but not the voltage value. Okay, so once we write it down, then we add the 2 reactions. When you add the 2 reactions, we can cancel out the 2 electrons here, 2 electrons here. We add up the copper solid, which we have got it here, plus 2 Ag plus aqueous, we've got that here. And then here we have, on the other side of the arrow, we have copper 2 plus aqueous on this side, so we've got that here. And then plus 2 Ag solid, we've got that here. So we've written that down over there. And then we just added up the 2 values. And then the net voltage output for the overall reaction comes out to be 0.46 volts. So this thing that we are writing here, delta E naught at the bottom, the value that we're writing right over here, this value, this thing is called the net potential of the reaction, net potential of the reaction. Okay, so these numbers that we are writing here, these are called standard reduction potentials for the half reaction. This delta E naught is referred to as the net potential for the reaction. So what we are doing here is basically combining the 2 half reaction. One of them is going to be the oxidation half reaction. The other one is going to be the reduction half reaction. We're adding them together and then get the voltage of the overall reaction. Okay, the net voltage that we are going to get from this reaction is 0.46 volts, and that's the amount of voltage we can generate from these 2 half reactions. All right, now we know that we've gotten the voltage output. Now the next question becomes, how do we convert the voltage into energy? Because whenever we run battery, we say that we get energy. How can we convert the voltage into energy? In order to convert the voltages into energy, we have to rely on a relationship that connects some thermodynamic parameters to this voltage parameter. So the thermodynamic parameter that we're already familiar with, if you've taken some thermodynamics, we know that this is the Gibbs free energy, or the standard Gibbs free energy. Gibbs free energy, because it has the naught on the top, this is standard Gibbs free energy. And if you want to relate the voltage that you calculated, delta E naught, to this Gibbs standard free energy, then we have to use this equation to do that conversion. So the way that works out is delta G naught is negative N times F times delta E naught, and where your delta E naught is the same thing that we calculated over here. This is 0.46. F that we're writing here is the Faraday's constant, and the value is given. It's 96,485 coulombs per mole, and N here represents the number of electrons involved in the reaction. So the N here is the number of electrons involved in the overall reactions. So how do we know the value of N? If you remember, when we wrote the 2 half reactions, when I showed them to you before, you see that the copper half reaction involves 2 electrons. And we see that the balanced silver reaction also involves 2 electrons. So that tells you that the N value is going to be equal to 2. So the N value is going to be equal to 2, F value is equal to 96,485, and delta E naught value is 0.46. You put them all together, and that you will get this equation, and you just multiply them all together. And then you have to remember that when you multiply 1 coulomb, which is written as C times 1 volt, you get 1 joule. So when you multiply the coulomb times volts, you end up with joules as the unit. So when you multiply all of them together, you will end up with 88,766.2 joules per mole as the free energy, with a negative sign in the front, because the equation says delta G naught is negative NF delta E naught. So you shouldn't forget that negative sign. There is a negative sign there. If you want to express this in kilojoules, this will be the value in kilojoules. We know that 1000 joules is 1 kilojoule, so we can convert the joules to kilojoules if you like that sort of units. And one important point to remember here is that whenever our delta G naught is a negative value, we know that if it has a negative sign, that means that the value is less than 0. So whenever your delta G naught ends up being negative, that tells us that this process is a spontaneous process. That means this redox reaction, where the copper reacting with silver ion, making copper 2 plus silver metal, this reaction does not require any external intervention. That is, you don't have to heat it, you don't have to do anything. You just you stick the copper wire in the silver solution, and it'll automatically produce silver solid, and it's going to produce copper 2 plus in the beaker. You don't have to do anything to make that reaction happen. But the one important thing to remember is, when we say the word spontaneous, all we are saying is that it doesn't require any external intervention to make the reaction happen. But it doesn't say anything about how fast the reaction will happen. The reaction could take, 10 minutes, 5 minutes, 1 day, 2 days. It depends on the reaction. But this delta G naught value tells you nothing about how quickly the reaction is going to happen. It only tells you something about whether the reaction is going to go from reactant to products without any intervention, or is it going to happen only with intervention. That's all it's going to tell you. So it provides no information about rates. It provides no information about rate constants. It only gives you information about the fact that it is possible for either your reaction to go from reactant to product, or if your delta G naught is positive, then it'll say that it's non-spontaneous. That means it's not going to easily get to your products, and that's what this is going to tell you. Okay, so what we have done so far is we've learned how to calculate how to use the standard reduction potentials to figure out which one is going to undergo reduction, which reaction is going to undergo oxidation. We figured that out. We also figured out the net potential of the cell. So this is, as I mentioned, this is called the net potential again. So this is net potential of the reaction. And then we also learned how to convert the voltages into free energies, delta G naught. And from the delta G naught, we also learned to predict whether this reaction is spontaneous or non-spontaneous. Okay, so we've learned all of these things in our discussion so far.